count. You didn't look at it? It said 1900.
Why were you looking at my work?
All right, party people.
You
So you guys had a little form last night.
I was like, why did she write so much?
Okay, so I want to review a little bit. Okay.
But it's only because I have like my sword.
I'll try to keep it down so you can hear.
Jada, you proud of me? I did this one all
Still don't have everyone coming in. I still have like 5 people not doing the firm, but I can't bring everyone to the water. Okay, so a couple of points I want to make is the delta G stuff that we're learning. Okay, so we're learning, hey, delta G equals delta H minus T delta S. And this, of course, is the system. This beautiful thing, little ditty right here. Beautiful equation that expresses the system's heat flow and the system's change in particle freedom to the overall what? Delta S of the universe. And this delta G, free energy, if negative, tells us that free energy was released in the process, which means we have a spontaneous process. If it's positive, it means we have to add free energy to the process to make happen. Okay? That's something we should have now. This is tied to the delta S of the universe, second law of thermodynamics. Okay. Now, if you notice, if we're going to satisfy delta G from tablature, then we're going to use heats of formations to get this value. Notice this little dot here. And if I use delta S's, okay, by subtracting the absolute entropies from tablature, this is going to be little dots here. Which means I'm going to be solving for the delta G with a little dot. Which means what? All I have from this equation is what the spontaneity would be only at these exact conditions, which we should know thermodynamically mean. This is important. That we have 1 atmosphere of pressure available. We're at 298 Kelvin, or 25 degrees Celsius. And that the concentrations at these conditions are either 1 molar if it's a solution, or if it's a partial pressure, 1 atmosphere. You must understand that. So this really is only good if I have those exact conditions. When do we have those exact conditions outside of a thermodynamically controlled laboratory? Almost never. So this is nice, but it's very, very limited because we're locked into those conditions. So to really use this, I've got to transform this delta G under standard conditions into a way to measure the delta G non-standard. Little circle there, no circle. That's important. Now I know sometimes I mess up in my language in my lectures, and sometimes in my derivation I forgot a little dot here and there. But that's what's important, okay? We're mostly on non-standard conditions. And where this is actually headed, my friends, in chemistry, is that there's even changes and shifts in reactions that we learned about. So that's why we're moving in that direction. Okay, let's get to the derivation, and I'm just going to highlight what this meant. Okay, and we'll go to the form. So the first and foremost is that when we get to derive an equation that's going to solve for delta G non-standard, that becomes really, really more useful than standard conditions for reasons I just explained, we start looking at dilution. When I take sodium chloride and break it apart into Na plus and Cl negative, or if I take a gas and make it travel into a bigger volume, those two conditions increase the particle freedom, okay? Think about it. I've got an enclosed container with these 4 gas molecules, and now I have a closed valve, but now I've got a what? Larger volume. If I open up this valve, what's going to happen? These molecules, okay, not all of them, but most of them possibly, will do that. And as molecules disperse into a bigger vacuum, bigger volume, you can understand, isn't there greater freedom? Isn't there a dispersion? Keeping gas molecules in a compressed area, isn't that a concentrated form of energy? And we learned last year in biology, diffusion goes from high concentration to low. Why? You have a lot of concentration in a small area. Doesn't it want to get out by the second law of thermodynamics? That's what really entropy is. People say entropy is what? Hey, in Regents chemistry, we say entropy is essentially just randomness. It's more than that. It's dispersion of energy. You keep stuff in a small area. Remember the mitochondria? I know it's been a while. Some people don't take AP Bio, but if you remember the mitochondria, we had this cystae. And what we did is and it looks like the eyes there, but no. But what we did was we pumped what? Protons into that intermembrane space using the high energy electrons that we got from FAD and NAD plus, right? So we pumped in electron transport chain a lot of H pluses. We created a concentrated place of energy. We made basically a what? A gradient, okay? A concentration gradient. Now we needed energy to do that, right? To take protons and stuff them in a small place, we needed energy. And we got that energy from the glucose, or the high energy carriers. And then what did it do on its own? It rushed through the ATP synthase and turned that turbine to make the ATP, okay? So if we've got a concentrated source, it's gonna spontaneously go to a less concentrated source. That is how it works. They call it what? Passive transport, high concentration to low. What is it really? The second law of thermodynamics. Delta S of the universe increases. You can't keep that down. So whether we have gas going into a bigger volume and diluting, this might be a what? Let's make some numbers up. A partial pressure of 1. This is a partial pressure of 0.2 or 0.1 or less. Entropy of the particles just what? Increased. And I do the same thing with what? I have a concentrated solution of salt water and I dilute it. Aren't the particles freer, more expanded out? Okay, if I was to take a large volume of water, okay, same idea. And this is an elementary education type of demonstration, but I have water, warm water, because you can see molecules moving, and you put a couple of drops of food coloring. What does it happen? What happens to it? You see the food coloring dispersing out, especially if it's warm. Why does it do that spontaneously? Because that's a concentrated what? Concentration gradient. We're going to go from high concentration to low. We're going to disperse that out. So entropy increases when you dilute, okay, a solution, and entropy increases when a partial pressure goes from high to low for the same reasoning. So that makes sense, right? Can a solid or a liquid, okay, change their entropy? Unless you're going to a different phase, possibly. But by itself, in a reaction, a liquid and a solid can't do that. And that's really important as we go through this. Okay, now that's just some background. So now what are we talking about here? Well, they figured out exactly, experimentally, how much it does so. So they take this non-standard entropy, measure of what? Particle motion, okay? Dispersion of energy, whatever you need to explain it. And this is the part for what? This is the system's entropy. We always talked about yesterday the particle separation equals the standard from tablature minus our natural log of what? The actual concentration over the standard concentration. What's the standard concentration? 1, whether it's a molarity or a partial pressure. Okay, so what's it become? So we did some math. We did it for a gas. And what do we have? Well, you can look at it the same way for a gas. If you do it for a gas, the concentration is moles. And how do we get moles over volume? PV equals nRT. We solve for N over V, which is molarity. So C equals that. So if you're doing for pressure, we put the P over RT. It cancels. And essentially, we can evaluate the concentration or the partial pressures. These both become 1 with that little knot there. Okay, and there we have our two what? 2 formulas. Okay, and there's our 2 formulas. Non-standard entropy. Why are we talking about non-standard entropy? Delta G is based upon entropies, correct? Come on, stay with me. So this is experimentally. Now why is this R constant? Because it's about the randomness of the motion of the particles. Why do we have an R constant in gas laws? Because we have to use the ideal understanding that what? Gases are totally random. So this is our what? Price per seat here. So there's our joule, R constant. Now, we can use this or this. Understand, and this is important, when we evaluate changes of non-standard delta G, are we in the area of gases, partial pressures, or are we using molarities? Okay, we use both. Okay, now, one thing I want to talk about, okay, is that some people have some issues with this, is that, what the heck is a natural log? What the heck is a natural log? Okay, log base E, fine. Now for those that say, what the heck, I don't know what that means. Well, let's start with something you do know from what? Let's talk about something you do know from pH, right? If I have an H plus or an H3O plus concentration, that's 1 times 10 to the negative 5. And concentration, get used to it, we use brackets. Brackets from now on in mean molarity. So the molarity is 1 times 10 to the negative 5. What does that mean? Well, what's the pH? Well, base 10, what does this mean? This is 0.1, 2, 3, 4, 5. That's the real number, correct? So we take the real number, and if I want to stuff it into a base 10, there's 5. Okay, you with me? So this is base 10. This means that I take 10, and I times it by itself 5 times, 5 zeros. In this case, negative 5, I move the decimal place. So base 10 logs are easy because numbers work in tens, you can just use decimal places. Now, what the heck is a natural log? A natural log is base E. Okay, now what the heck is E? I'm asking you. What's that? This is a log. Listen, remember we did this?
Exponentially.
Yes, well, so is this.
But
So is this. I can do an exponential growth base. Listen, to me to go pH, what do I do with this? Negative log. First of all, what's the log of this number? If I say what's the log of this number, what does that mean? Put that number into an exponent that's base 10. That's what that means. Now, log is just whatever that is. There it is. Now, in pH, what do we do? Negative log to make it what? Positive. So the pH is 5 there. So when I say log of 0.00001, what do I get? Negative 5. Well, natural log is the same thing. And I take some number, natural log of, let's do 0.00001, and I get some other number because we're using a different base. The base is not 10, the base is E. What is E? No. Okay, let me help you, because it's unfortunate you guys are doing this math, but you don't know what it means. I can compound, people are saying compounded money and everything else. It's true. We don't use base 10 for compounding of money. We don't use base 10 for natural logarithm scenarios. Let me explain what base E is the most simplistic way, and I should not be the one explaining this, right? You've had this before? It's the same thing, we have a different base. This is base 10 to what? Some x. This is what? E to what? What the heck is E? Okay, that's unfortunate. Let me help you. What happens when y equals x squared? Because you said exponential growth, so can this be. So let's make this 1. So when x equals 1, 1 times 1 is what? So I have this. So when we have 2, 2 squared is what? Okay, when it's 3, 3 squared is what? Okay, and there's your what? Exponential growth. It's going to go up like that. Well, you can have that kind of exponential growth when y equals what? 10 to the x, right? Okay, of course, you're going to start with tens, but it'll do the same thing, correct? So don't say exponential growth because you can have it, but we don't use the growth of money unless we're using x. So let me explain. I want you to understand where this comes from because it's going to pop into your science. Let's look at it this way. Let's make a graph. Okay, let's talk about cells. Okay, this is natural exponential growth. Why do they say natural? Because in nature, we see this type of exponential growth. If I have a cell that cell potentially can divide into what in mitosis? 2 cells. These cells can do what? Become what? 2 cells. And so, although it looks like it's linear, if I do what? These cells grow. If these cells become 2, I got to do what? Make room for it, don't I? So this is going to be exponentially. So I don't see it going up, but notice this has to point down. See how I'm growing cells downward? For the total number of cells, I'm going to have to adjust this up. So this is going to bend upward. Natural logs are for exponential growth of one thing becoming 2, that other thing becoming 2. And so if you have $1 becoming $2, hey, that other dollar now can grow, and so you use it for growth of money. But forget that. For the growth of living things, one cell becoming 2, that every cell becoming 2, you get a natural growth of bacteria. You can actually predict with natural logs, okay, what the amount of numbers of bacteria will be in 24 hours based upon this idea. Now, is it perfect? No, but if you have tremendous numbers, it actually approximates those values perfectly. Someone figured out what this base is, and it's 2.8, 2.71. Okay, I don't know exactly because I'm not going to memorize something. But so the base of E is really what? 2.7, I think, or something close to that. And no one likes that, so they just put an E there. And they say exponential growth. Well, all of these are exponential, but this is exponential growth of natural things. Now you say, well, where is it coming for chemistry? Well, this is about the random motion of stuff. If one molecule hits another, couldn't that one hit another? So one molecule just affected 2. And each one of those can hit another, correct? Now, it's not perfect, right? Sometimes one won't hit another one. But if you're talking about Avogadro's number of cells or particles, it approximates the motion very, very well. So in nature, the amount of growth of cells, or one particle hitting one and that one hitting another one, they all affect each other. So one molecule eventually can affect the what? Motion of all the other molecules, correct? So that's where it comes from. And that's what we use. And you don't have to know that, but you know that you're using a different base based upon how molecules interact. I wanted to do that for you because people just blindly do, oh, time to do natural logs. I don't know where they come from. Okay, it works nicely for growth of money because $1 becomes 2, and each of those now can be compounded, and that's how money grows at interest rates, and you can do that as well. But that's where it comes from. Don't let someone just tell you something. Stop them and make them explain where that comes from. So we see that now. Okay? And if they don't like it, too bad. Challenge your teachers, darn it. Okay, so real quickly. All right, here we go. So we got all of this. Now, this part we talked about that, wait a minute, I'm not limited. Tonight's homework is part of this. I'm not limited, party people. When I do delta G, I can solve for when a temperature will become spontaneous. Now, think about it. We know that temperature, the conditions should be 298. But if everybody else was measured at standard conditions, and I change the temperature, if I change the temperature of the reactants and products, aren't I going to change their entropy equally? If I make them go faster, they're going to move more. I'm not talking about a chemical reaction. So we can solve for a temperature at which this will become spontaneous. And you'll say, whoa, why do I want to do that? Well, when some reactions we're going to get there are close to equilibrium. Burning paper is not close to equilibrium. The reverse process doesn't exist. But when we have delta G's that are small, -11, not -1,000, they're a little bit spontaneous in the forward, which means that the reverse is an extreme possibility. The reason why they're not very spontaneous in the forward is that the spontaneity in the reverse is what? Pretty good as well. So things that are close to equilibrium are going to have small negative delta G's. Now, what if the delta G is -10? That means the reverse is a little more spontaneous than the forward, correct? Delta G's measure the forward spontaneity. That's just how they start. So if the forward is +10, then the reverse is -10. That makes sense? So if I have something that's not spontaneous, but it's positive, it's close, in order for it to become positive, right? So here's my number line. Here's 10, here's 0, here's negative 10. In order for this to become negative, doesn't it have to pass through 0 first? So I'm going to set my standard delta G to 0 and then solve for the temperature. And that'll tell me the temperature that I have to increase or decrease based upon what delta H is and everything else to make this get into the what? Negative area. So that's the breakthrough point. So sometimes you'll see AP questions, and you'll see one tonight in one of your homeworks with the lecture, okay? That won't be on your quiz test tomorrow, okay? So that's important. Let's continue on. Okay? Now we got these, and this is going to go fast. I got these reactions. Let's do for gases. Bottom line, if I'm talking about gases, party people, parentheses. Okay, notice number 2, which is the partial pressure. Okay, parentheses. Okay, which are is partial pressure? Don't I have 2? Yeah. Okay, brackets are what? Molarities, and this doesn't make any sense. Okay, why do I do that? Because you can get a point wrong on the AP if they ask you to write an expression for things that are gases and you write brackets if in fact they're partial pressures. It's so silly, but it's easy to forget. So I'm just kind of reminding you, good job for getting that right. Now, what about this one, number 1? True and false. Adding water to an enclosed container will increase the entropy of the gas above the water. If this is my container, this was not good. Okay, now if I add water, what's happening to the space for the gas molecules? So is it in fact this space becoming smaller? Isn't this gas getting compressed into a smaller space? Aren't I really concentrating the energy by putting the gas molecules into a smaller space? So the entropy is what? Decreasing as I make this partial pressure go up. What we learn? When partial pressures drop and gases expand, the what? Entropy increases. Entropy is the what? Dispersion of energy. You're making this concentrated. That's why this answer. Yes, Mike. Number 2, this is just a straight fact. When we write partial pressures, we write parentheses in our expressions. When we write concentrations, molarities, we write brackets. Brackets, parentheses, I'll get that right. So this is for partial pressures. This is straight for molarities, concentrations. Okay? That's just something that was directly from that. Okay, now let's continue on. All right, so I got this reaction. What's the whole point of this? The whole point was to what? Find non-standard delta G, but I've got to go through what? Non-standard S first, because what is delta G? You're really measuring the delta S of the universe. So, what did I just do here? I put this into our what? Formula we got experimentally. Okay, then what did I do here? Delta S of the reaction is what? Products minus reactants. So I took this, and notice I times it by 2. Why? Products is what? Look at your reaction I gave you. This is called, here we go. Look at here. So products, hey, 2 times ammonia. Where's ammonia? Right here. So 2 times that. Then it was minus the what? The total products. Who are the products minus reactants. The reactants, N doesn't have anything. That's this one, and the one that has 3 is the hydrogen. And what did I do? I put them together, put all the logs together, and I left the expression. Well, wait a minute. Wait a minute. Products minus reactants? Oh, the S is this? Isn't this the delta S of the reaction? Non-standard? I mean standard? Right, we just learned? And then the rest of this becomes this expression. And we use 2 properties of logarithms. Okay, and I'm not going to review that. But what happens is what? What do we get? Delta S of the reaction, non-standard, equals the standard we get from tablature minus our natural log of this thing. Now this thing, party people, is called reaction quotient. We're going to live with reaction quotient. It's called Q. Now, Q, and this is important, Q, party people, is products, concentrations, or partial pressures over reactants. Coefficients become exponents. Solids and liquids do not apply. Q is products over reactants, coefficients become exponents. How did that happen? How did the coefficients become exponents? Because we did what? We used a logarithm property, didn't we? Remember this was, why was this squared? Because that was a coefficient using another logarithm property, right? And then we used another logarithm property to make this what? Okay, so we used two logarithm properties to put the coefficient in the reaction, basically becomes the exponent. So products over reactants, coefficients become exponents, solids and liquids do not apply. Products over reactants, coefficients become exponents, solids and liquids do not apply. Products over reactants, coefficients become exponents, solids and liquids do not apply. Products over reactants, coefficients become exponents, solids and liquids do not apply. Products over reactants, coefficients become exponents, solids and liquids do not apply. I can't hear you, I won't feel it. Products over reactants, coefficients become exponents, solids and liquids do not apply. That is called how we measure Q. You will mess that up. It's right here. Okay, now, party people, why did I ask you? Why did I ask you to find? It seemed like a mean thing to do. Why? It seemed like a mean thing to do to ask for what? What the time code when I first said coefficients to exponents. I wanted you to look for it. I wanted you to know that coefficients, products over reactants, coefficients become exponents, solids and liquids do not apply. That might be 2 or 3 points on your AP. And it equals what? Reaction quotient. Now, if they're what? Partial pressures, they become parentheses. If they're concentrations, they're brackets. And what does it tell me? It tells me how much the reaction's concentrations have diluted or expanded. It tells me how, in this case, it tells me how the gas has changed from standard conditions. Oh my gosh, it tells me how far away I am in terms of the entropy of my what? System is away from its tablature. Remember, what was the conditions for S when you do this absolute entropies? 1 molar if they're brackets and concentrations, or what? 1 atmosphere. If these aren't 1 atmosphere, now notice, what are these values? Well, you measure the actual concentrations and you put them in. This is actually an equation called a reaction quotient that we measure. And think with me for a second. If we've got a lot more products than reactants, isn't this going to be a big number? And then we're going to get times a negative. Think with me for a second. If this becomes a bigger number up top, these should all be 1s, shouldn't they? If we're at this condition, correct? But a real reaction's not going to be at those conditions. So if I measure my reactants and products, in this case partial pressures because I see parentheses, it won't be 1. And if there are more products than reactants, this will be greater than 1. I times it by a negative number, I'm going to subtract that. Because if I've got more products, does it mean something expanded? Or I'm sorry, something got compressed? Think about it. My partial pressure now is 2 here. Didn't I compress something? Didn't I concentrate it? Did entropy increase or decrease? Right. That's not good. So I made my what? From tablature, decrease in entropy. Hey, if this whole expression is less than 1, doesn't it mean the gas has expanded into a larger volume? Doesn't entropy increase? So if this number is negative, hey, what's a log of a negative number? Okay? Think about this. If I've got a number, my bad. If I've got a number less than 1, isn't that this expression going to be a negative log? If I have 0.001, isn't that 10 to the negative 3? If I've got a number less than 1 because these guys are bigger now, isn't this expression right here going to be a negative value? Hey, don't get lost. Whether it's 10 to the x or e to the x, a number smaller than 1 gives you a negative exponent, correct? So this expression goes negative. What's negative times negative? Positive. You're going to add to the delta S because they've expanded. That's how it works. Now, last little piece. Okay, here's my Q. And what did I do? I plugged this in. Hey, I write delta G, non-standard. My standard equation. I took this and plugged it in for delta S. And what do I get? Delta G non-standard is delta G of the reaction, that's this right here, plus RT ln of Q. That's your new formula. Delta G non-standard, no dot, is delta G from tablature plus RT natural log of Q. Okay, R is a gas law constant in joules, temperature in Kelvin. Okay, now I just explained that. Now let's go look at this. Boom. Hey, when the reaction code is equal to 1, hey, what's Q equal? Products over reactants. Coefficients become exponents. Why don't solids and liquids apply? If my reaction has a solid or a liquid, why don't I put it for my Q? Can a solid really expand enough to really change its entropy? No. Can a liquid have a change of entropy? No. You can't, a solid can become a liquid, that's a different story, but the solid itself doesn't have a molarity, doesn't have a concentration. Does a pure liquid like water have a concentration? No, no. So when we evaluate Q in our reaction, we look for gases or aqueous, which means solids and liquids do not have a value that I can measure for how the concentration, what? Changes. We have to look how concentrations get diluted. This does not, a solid has no concentration. What's molarity, party people? Molarity is what? Moles of something dissolved in what? Liter of solution. This is a mixture. When I have salt water, I have salt with water. This is just one thing. What's the concentration of a pure solid? Doesn't make any sense. It's not a mixture. What's the concentration of a liquid? Doesn't make any sense. So when you write this expression, if you have a liquid or a solid, you do not include it because you can't measure its change in entropy. This is about dilution of a gas or an aqueous, right? Okay. So when the reaction quotient is equal to 1, the non-standard delta G is equal to the standard delta G. That's true. Think with me. It's a natural log of 1. 0. Which makes this whole expression go to this. So that part is true. Okay? Now the next statement. The Q equals 1 when all the concentrations are at 298. No. That's false. Q equals 1 when all the concentrations are at their standard concentrations, which is what? 1 molar, which if it's a aqueous, or 1 partial pressure, ATM. It's not at being at 298. Okay? Because if you have what? 1 over 1, I don't care what the coefficients are, it'll be 1. Okay? That's why that was it. Okay? Too many people got that wrong. Okay? This is only part of the conditions. Remember, this measures the concentrations. Why? Because if they change from 1, S is going to change. And delta G measures S. Okay, the most important question was the last, because this is where we're headed and how we're actually going to use this. Okay, and this was the worst. Okay? And by the way, as poorly as you may have done, there are people out there that struggled, fought, scratched, and got hundreds on this. Now maybe you didn't have time because maybe someone else gave you busy work. I'm not. This is essential. Like an essential oil. In fact, no essential oil that you buy is essential, okay? But I'll tell my wife that. Okay. Now, sorry for my OCDers out there. Is that better?
Oh, I thought you talked about this.
Oh, yeah, now we're working. Ooh, damn. Ooh, that's okay. Now, if the products are very large compared to the reactants, the reaction Q is what? Let's think about this for a second. If the product concentrations are very large, what's Q equal again? It's a reaction quotient. It's products over reactants. Coefficients become exponents. Solids and liquids do not apply. In this case, because I wrote, in this case, brackets, what do I have here? Molarity, concentrations, which would have to be what phase? Aqueous, solid, liquid, or gas? Aqueous. Aqueous and gases only go in this expression. So, if the products are very large compared to the reactants, Q is going to be greater than 1, correct? You with me? If Q is greater than 1, correct? What do we know? Non-standard delta G is equal to standard delta G plus RT ln of Q. If Q is greater than 1, what's the natural log or the log, who cares, of a number greater, it's going to be positive, right? 10 to the 2 is 100. So 100, the log of base 10 of 100 is positive 2, correct? So this becomes a what? This becomes a positive value.
It is plus.
Yeah.
Yeah.
Oh yeah. It is.
Okay, my bad.
Oh.
So
No, you were good.
plus plus gives me a what? If this is a positive, now it depends where we're starting here, right? This delta G could be positive or negative. But let's talk about this. If they are very large, okay? If the products of the are very large, okay? And we have more products than reactants, the reaction quotient is what? Well, okay, very large, okay? And what it'll do is make RT become positive, correct? This whole thing is positive. Okay, so this factor now becomes hugely positive. Okay? Now, what do we have here? Making the non-standing becoming non-spontaneous. Is that true? Could that do that? If this factor gets so large, we may be starting negative, but couldn't this positive overtake this negative? So if this factor gets so positive, you can say that it's going to drive your non-standard delta G to become what? Positive. Now what does that mean? Delta G is about the forward reaction. So we've got a delta G that could be what? Spontaneous? But now it's going to be what? Non-spontaneous. Potentially makes, so this is true, potentially making the non-standard delta G become non-spontaneous in the forward direction. True. I say potentially because it's about the size of this, correct? Shifting the reaction in the reverse direction. Ooh! Remember that? If you've got X plus Y gives me an equilibrium possibly, XY, and I do what? Increase my products. What'd you guys learn? What did we learn? Here's my shift, here's my response. If I increase XY, isn't there going to reaction going to lower XY to maintain equilibrium? Because everything works. So we're going to shift where? How? We're going to lower it. If I'm shifting to the left, isn't the reverse more spontaneous? Isn't the reverse going to get negative? Which means the forward, this measures the forward gets what? This is showing us that we're going to have a shift in the reverse direction. This is Le Chatelier's principle. Didn't we talk about this? Now we're defining it. One more. Not forward. Making non-standard delta G become spontaneous for the reverse reaction. If we're shifting this way, this delta G is negative, which makes the forward what? Positive. That's where we're headed. We've learned this already, but now we have the details. Okay? Now, you will have a bonus question on this material for your test tomorrow. But your test is on the skill set that I provided. We're going to go a little forward tonight with the lecture. Just follow me along. There's some skills I want you to see in there that you should know, but there's some things that I'm teaching you tonight that's new, okay? But please, review the skills from the fake test I gave you, that key, okay, and all those little problems, the pitfalls I talked about.
Is the test going to be?
It's going to be front and back, a lot like what you saw. The skill set, one period, front and back, okay? Tonight's homework, a piece of it, like using delta G's of formations, I'll explain. Okay, but no, the skills that we're moving forward using this equation will not be on it. I will have a bonus question based on this. So therefore, it's not, you don't have to know this. But if you do, you'll be rewarded. Bye-bye, guys. So this is the what? So this non-standard delta G is actually the what? Le Chatelier's equation that we learned in September. That's the point. It all connects. Bye-bye. I start with my clothes tucked in, but I do.